where the electroweak symmetry is restored, so your Higgs is pushed back up to the symmetric point in this vacuum by some sort of dynamics. Or more generally, they could also be, you don't necessarily have to just consider electroweak symmetric. You could also just consider some non-trivial change to the electroweak vacuum. And I'm gonna, if time permits, I'm going to talk about two different kinds of relics. There's a high likelihood I'll probably only end up talking about the first, which is inside of strong magnetic fields, and in particular, if you have magnetically charged black holes, then you can have essentially just with standard model and general relativity, you can have these sorts of things. If there's time, which there very well may not be, I will also talk about how if you have Higgs portal couplings to some macroscopic states in the dark sector, like topological defects, you can also have these sorts of relics. And of course, the main focus will be on what is the phenomenology that you get from these sorts of relics. So let me tell you a little bit first about magnetic black holes and just some of their general properties before we get to the pheno. So you can write down the solution or the metric for a charged black hole, which is just the Reisner-Nordstrom metric. And for reasons that will become clear in a few slides, I'll take these black holes to be pretty close to extremal. So what that means is that the mass in some suitable units is equal to the charge of the black hole. And when this happens, there's a lot of interesting properties. The temperature goes away. A lot of other things happen, but for now, the main thing to note is that when I go to this limit, there's this really strong magnetic field outside of the black hole, and if you look at it right next to the horizon, as the charge is decreasing, the magnetic field is growing, and that's just because of this because the radius is directly related to the charge. And so if as this magnetic field grows and grows, as you're taking the limit of charge getting smaller, you have a lot of interesting effects with large magnetic fields. And these are, and in particular, this goes by the name of Amyorn-Olson condensation.
Can I ask, what is being held constant here? If the charge, if I take the limit that the charge goes to 0, it looks like the field.
So I'm not going to take the limit that charge goes to 0 here. I'm going to keep this Q to be an integer value, respecting essentially Dirac quantization. So there's, and really when I say like in this limit, I'm just saying like as the charge gets smaller, but if you're keeping things extremal, so if you're keeping the mass and the charge related in this way, then then the B field is going up.
But do you have magnetic charge, or is this is just a normal B field due to the electric charge?
Yes, this is so you can of course write this down for an electric charge. But you can also write this down for a magnetic charge. And so here in particular, I'm considering this being a magnetic charge.
I see. Okay, so this is not okay. So this is a magnetic charge that's producing it.
That's right.
Okay. It still seems a little bit counterintuitive that the charge going to 0 makes the field get larger. I guess this is the field at the horizon, and the horizon is getting smaller at the
That's
same
right. That's exactly it. It's that the event horizon itself is shrinking, and it's shrinking proportional to Q, so that overall this ratio of Q on R squared is getting larger.
Okay.
Okay, so once this magnetic field becomes large enough you get some interesting effects. So you have these Landau levels where you have these particles essentially orbiting around magnetic field lines, and you have this quantum effect where you have all these various modes of quantized orbits essentially around the magnetic fields, and so the field itself ends up giving a contribution to the mass terms of your fields, specifically the mass terms of the boson fields. So the first kind of interesting thing happens when the field becomes of order the W boson mass, and you can see at that point that the W boson mass gets a negative contribution to its mass, and so it becomes 0, and so you start to have condensation of W bosons. And then further, once you go just a little bit higher to the Higgs mass, then you get some positive contribution that would cancel out the negative mass squared contribution from the Higgs. And so as a result, you overall get now a positive mass squared term for the Higgs, which means that the Higgs prefers to sit at the origin where the electroweak symmetry is restored. And this happens for very high field values, 10 to the 24 Gauss. But because of this relation that the B field in this previous slide is at the horizon is increasing as you take a smaller and smaller Q, that means that for any nearly extremal black hole, there will be some electroweak symmetric region as long as the charge of the magnetic charge of the black hole is less than about 10 to the 32. So a very large value. And so we can show a picture of what this looks like, and this was recently, this whole phenomenon of how this happens around a magnetic black hole was recently pointed out in this paper by Maldacena over the summer. And so and that's what this figure is from. And so what this picture is you have some very small black hole with some event horizon radius, and then out at some much larger radius, you have this whole region where the Higgs Vev is exactly 0. Then you have some small ring where you have some W boson condensation, but still non-zero Higgs Vev, and then finally out in the rest of the universe you have the normal electroweak symmetry breaking that we're used to. The other thing to note is that because of the electroweak symmetry restoration, in the interior here, the U1 Y force, the hypercharge force, is the one that's the most relevant, right? As opposed to the ENM force, which is this missing between SU2 and U1. So that gives some small correction actually to the mass. So you get some cosine of Weinberg angle to the mass that won't end up being too important for our discussion, but it gives some more interesting effects in there. And then finally, you can of course calculate what the radius is for the electroweak symmetric region, and this is going as the square root of Q and in units of the Higgs mass. So plotting these two radii, the black hole radius, event horizon radius, is shown down here in blue, and of course it's growing linearly with Q, whereas the electroweak symmetric radius is growing as square root of Q, but is much larger, especially at these lower values of Q. And here the mass is assuming again that you have an extremal black hole with this charge. And you can also see.
Excuse me, I have a question. What's the reason for taking the black hole extremal? Did you say?
Because yeah, I'm coming to that in just 2 more slides.
Yeah, because normally you have an inner and outer horizon, right? And
yeah, I'm going to come to that in just a few more slides. If you will bear with me for now.
Yeah, sorry. Okay, yeah.
No, it's fine. Yeah, but I will point out that it's somewhat related to your question. You of course don't have to take the black hole extremal. You can see that if I pick some charge, say 10 to the 22, but then instead of having the mass, sorry, let me go smaller, 10 to the 10. But then instead of having the mass be only 10 to the 2 kilograms, if I instead have it be somewhere up here at say 10 to the 20, there's still the electroweak corona still has a much larger radius than the black hole, even for a non-extremal black hole. So you certainly do not have to have an extremal black hole to have a corona radius. But in a couple of slides, I'll explain why I'm mostly talking about extremal black holes.
Yeah, but that was the limit that Mulder-Senna took, was extremal then?
Yeah, for the same reasons that I'm about to explain.
Okay, yeah, okay, fine, sorry.
Okay, and then finally, the place where these two are equal and where you no longer have a corona is this, as I said, charge of about 10 to the 32, and that corresponds to a black hole, if it's extremal again, having a mass of about the mass of the Earth, so 10 to the 27 grams. Okay, so now I'm going to start inching my way towards explaining why these need to be extremal. So far I've only talked about the boson modes, the W and the Higgs, but let's take a little bit closer look at what happens with the fermion modes. So the Sarah model fermions are massless. Of course, because the electroweak symmetry is restored, there's no contribution from the Higgs vev, and then there's also additionally no contribution to fermions from these Landau for the lowest Landau level. And so as we'll see, there are two interesting effects with these massless fermion modes, or these massless fermions. There ends up being some factor of Q, which is the charge of the black hole times the charge of the hypercharge of the fermions, degeneracy in the modes of this lowest energy Landau level. And these Qy times Q degenerate modes propagate only along essentially the radial and time directions. So that's why I call them 2D modes. So let me explain a little bit more what I mean by this. So if you write down the metric and you want to get to what the Dirac operator is in this metric, and write down the gamma matrices in this spinor representation for 2x2 spinners, or two-part spinners. And if you write it down in this particular way, then you see that you get some separation of variables, where on the left-hand side of this product, you only have functions and derivatives that are functions of t and x, and on the right-hand side, you only have quantities that are functions of phi and theta. And so if you then take a separation of variables ansatz, saying that you get these two component spinners, one depending on t and x and one on theta and phi, and you simplify the Dirac equation, you of course can write these down as two independent equations. And if you solve the angular equation, you get something that depends essentially on spherical harmonics, and there are q different solutions for m ranging from -j to j, and j being related to the charge. So there are q different modes for angular modes, and so you have essentially these q different modes that are only propagating along the x, which is the radial, and the time directions. Yes, so that's what I just said. So finally, we can get to this question, the answer to this question. So if you have a non-extremal black hole, which has this electroweak-symmetric corona around it, then the Hawking radiation is going into these 2D modes. And this enhances the evaporation rate by quite a bit compared to the normal four-dimensional Hawking radiation. So whereas the four-dimensional radiation goes as the Schwarzschild radius squared times t to the fourth, which is parametrically just the temperature squared. The two-dimensional modes go only as temperature squared and then times the number of modes, which is enhanced by this factor of Q. And so what this means is that while a black hole that is 10 to the 15 grams that doesn't have any charge has a lifetime of order the age of the universe, i.e. the amount of time that it takes for the black hole to radiate all of its mass energy away. Similarly, a black hole with an electroweak-symmetric corona has a lifetime of only of order milliseconds to decay back to near extremality for some order 1 deviation from extremality. So this is essentially why at the beginning I started out by talking a lot about extremal black holes, because the Hawking radiation is so much quicker. It's much easier to get to these extremal states. And then, of course, finally, once you get near to extremal, so for the mass compared to the extremal mass, which is related to the charge, the temperature is suppressed by the difference here, and the black hole becomes approximately stable once it reaches this near extremal. Of course, it doesn't ever go exactly to extremal; it approaches it asymptotically.
Can I ask a super naive question?
Yeah.
That you might have commented on it, I might have just missed it. How do you ever get a charged black hole physically? Like, where does it come from?
Yeah, I did not comment on it, so you're right to ask. I will talk a little bit about it. There's kind of two things that you can say about this, though, off the bat, which is one, hypothetically, all I had to do was write down a metric here, at the beginning and say, okay, this metric exists. And so, in just the standard model in general relativity. And so we should be just intrinsically interested in that, right? This is just.
Yeah, I completely agree that as a theoretical exploration, it's very interesting. I was just curious if there's some astrophysical argument that these things might actually be produced in our universe.
Right. So if in addition to this, if also say gut monopoles existed, then it is possible for black holes to absorb those gut monopoles and thus carry some magnetic charge. And I'll talk a little bit more about that in a few slides.
I see, but how do I put this? If you do have gut monopoles, there are presumably not that many of them because of inflation.
So actually, this is getting ahead of myself, but yes. So there is this, of course, the cosmic monopole problem, and actually, this is actually a solution to the monopole problem. Rather than having them inflated away, you can actually have them absorbed by black holes in order to get rid of them.
I see. And is another possible answer that, like, forget astrophysically producing these things in I don't know, but maybe like they're left over from the Big Bang and somehow they were made in the Big Bang with a large magnetic charge and now they're sitting around and you're asking about their properties.
Yeah. So I think not enough. I have not done enough thinking, and other people have thought about this, have not necessarily done enough thinking about what all the possibilities are for how you could produce these things. So I think there probably are other ways to do this. I've kind of talked informally with collaborators about, like, maybe you have some monopole anti-monopole connected by a Z string, and then somehow you break that Z string by absorbing one of them in a black hole. I mean, so some kind of crazy things that we haven't really worked out. But yeah, so all this to say, like, yeah, there's a lot of crazy ways that maybe you could think to form them that maybe we haven't even thought of yet. But we should be inherently interested in whether these exist and what their phenomenology is if they do.
That's very interesting. Okay, yeah, I'm perfectly fine with theoretical explorations. I just curious if there was some more.
Yeah, I'll talk a little bit more about this in a few slides.
Awesome, thank you so much.
When you said that this is an alternative solution to the monopole problem, how are you actually getting rid of them?
So This was work done by Katie Fries about 15 years ago, which is basically you sweep up all the monopoles like in the black hole. So you get the black holes to absorb all these monopoles, and the black holes only carry mostly cancel out the charges within themselves, and they just get some net residual charge, and then you're left with very few monopoles outside of black holes.
But I still don't. The problem with the monopole problem was that the density of monopoles, given their mass, was too high, and they give larger. So, but where is that going? Are they?
So they get absorbed into the black holes, and then the black holes themselves, of course, they're not extremal when you first form them. So as they're absorbing charges, they're also evaporating away. And so if you have some black hole that even as it's absorbing charge is also evaporating, evaporating away, then you can get rid of all of the energy density from the monopoles in this way.
But are you losing? Is it absorbing monopole anti-monopole pairs, or is it?
Well, it's not pairs necessarily, right? It's absorbing monopoles and anti-monopoles, right? So on nets, you would expect it to have
magnetic charge that way. I mean,
right, exactly. You have some. It absorbs a positive charge here, a negative charge over there, and overall you're canceling out all the charge inside of the black hole.
And is it clear that enough monopoles end up in black holes this way? I mean, you would think, because the density of monopoles is going to be pretty uniform. Why do monopoles preferentially end up inside black holes rather than just staying outside black holes like ordinary matter?
Let's see. I would need to consult that paper to remember exactly like what the requirement is on like the black hole abundance. So it's possible that they assumed essentially like black hole domination at some early point before they evaporate away. I don't remember exactly. I'd have to consult the paper to know exactly what the relationship had to be for that.
Okay.
And I have that reference later on, if you're interested.
And just another question, as a matter of principle, also, I guess this charge, I'm not sure what you're going to do with these black holes, but could it be also some other kind of dark charge, not necessarily QED?
Yeah, definitely. Yeah, so that's something that I thought about in an earlier paper before this one. And so yeah, you could even think about this as ordinary electric charge, right? And then you could say, okay, well, you could get extremal stable black holes just with electric charge. That sounds like that could actually work, except it doesn't quite work because you also have Schwinger pair production, which is that you have these really, really strong electric or magnetic fields outside of the black hole. And so inside of those really strong fields, you can pair produce electrons and quickly discharge your black hole that way. So then you consider instead some dark charge, as you said, and yeah, that's something that was in a previous paper of mine.
Okay, interesting.
Okay, good. Okay, so yeah, this is kind of summing up what I've said so far. So unlike ordinary black holes, extremal black holes, once they reach to their near extremal state, are approximately stable up to these Schwinger discharge rates, which as long as the charge carrying particles are heavy enough, can be suppressed. And so while normally when we're looking at ordinary primordial black holes, we have all these various constraints, microlensing, evaporation. We normally cut off the plot here at about 10 to the 15 grams, which is, as I said, where the lifetime of an ordinary black hole matches the age of the universe. But now, in principle, we can open up all the way down to the Planck scale, and really, there's not very many, if any, candidates for dark matter like relics. in kind of this mass range. So it also happens to open up an interesting and different mass range for relics that we're not typically we don't typically think about, especially when we're thinking about just particles as opposed to composite states. Okay, there's going to be I'm going to preview essentially two interesting things that can happen for phenomenology, which are going to come back later as we talk about how you would know whether these relics exist. So one interesting thing that happens is once you have two nearly extremal black holes that are oppositely charged, if they merge, then of course they become non-extremal. And here I'm not going to consider the case where they happen to be exactly the same charge. I'm going to assume that there's some slightly different charge between the two, which is the kind of the generic assumption. In which case, you have some imperfect discharge. So you still have some Electroweak-symmetric corona, and you still have this very fast and essentially decay process once they merge. So you have some merge and then some very immediate Hawking radiation. The Hawking radiation is of course extremely high energy. So here, this is for a mass of 200 grams. And you can see the mass dependence here, and also happens extremely quickly, as we've already said. So looking for places where these black holes tend to congregate and merge is going to be one way that we can look for these relics. The second way that we can look for them is a process that I'm kind of calling Baryon number violation, which is that if a particle enters the corona, it gets directed down to the black hole event horizon because of the dynamics there with these 2D modes.
Excuse me,
Yeah.
turning to the previous story, wouldn't be advantageous for them to merge in the early universe? Like when you create, why would this process not? Like if you take WIMPs that annihilate, right? They annihilate much more happily in the early universe than now, right? So the same merging story would occur more happily in the times when the density is high.
Right. Excuse me. So there's a lot of research on this sort of question actually, because in particularly in light of LIGO, because a lot of people were interested about what is the rate of mergers of black holes at LIGO, and whether those could be primordial. And what the story is there essentially is that you may think that if you have two black holes that are close to each other, that they would be attracted to each other and merge immediately. And probably that happens for some of them, but for what happens for most of them is that then you consider the effects of other nearby black holes. And I should say, by the way, these black holes, they don't really see this attraction early in the universe, like a WIMP annihilation does. You may be thinking, maybe not, but you may be thinking, oh, they have these large magnetic charges, so the attraction between them must be huge. But it's actually not. It's the force between two oppositely charged extremal black holes from the E&M contribution is equal to their gravitational attraction up to this cosine theta W.
I think Maxime was just referring to the fact that the rate is going like the density squared, and the density is falling like 1 over the scale factor cubed. So the density, the rate of collisions is just going to be higher because it's n squared. And Maxime, you can correct me if I'm
Yeah, sure. But Nicholas is trying to finish the argument why it's not that high in the early universe. That's
well, the density has to be, unless
the density has to be, right? I mean, there's no.
Sorry, but the density is these are redshifting like matter, right? So the density is actually very, very small in the early universe if you don't want them to completely overclose things today. So these are much more massive than a WIMP, and so the number density is just very suppressed compared to that. So you don't really get very many meetings in the very early universe like that. And also their velocities are small, right? They're not relativistic. Maybe that answers your question.
Oh, okay.
Right. Yeah. I mean, just to finish the story, they really don't even start to move towards each other until close to matter radiation equality, when they can really kind of start to see each other gravitationally around all the other mess of plasma that's surrounding them, where the plasma is much more dense than these little black holes that are that aren't that don't contribute very much to the energy density at that time, prior to matter radiation equality. Okay. Okay. So yes, I was starting to tell you about the second process. Besides mergers, if you put a black hole in a dense environment, essentially, it's going to start sucking in all of the baryons and leptons in that environment, and when it does, then of course it deviates away from externality and can very promptly evaporate back into, for example, electrons. And so, for example, even if it absorbs a single proton, it has a prompt decay back to near extremality via electron if it's 2 kilograms or less. And so if it's above this, then you need more than one proton. But if you have some steady state of if you're in some dense medium and have some steady flux of particles going in, then you can end up having some steady amount of energy being radiated out. So so this is what I mean by baryon number violation effects. Separately, there is also some other interesting baryon number violation that I'm not going to talk about, which is that sphalerons are active inside of this electroweak-symmetric corona region, and very recently this paper talked a bit about sphalerons inside of these high B field environments. Okay, so let me try to fill in just a little bit more about the formation story. One possible formation story. As I said, there could be several others. So the idea is that maybe if you form black holes primordially, then you can have them absorb some amount of charge and be left with some residual charge. So in order to form primordial black holes, you need something non-trivial to happen with the quantum fluctuations that are generally seeded during inflation that give rise to all the structure formation that we see today. So while you measure some density fluctuations that are on the order of 10 to the minus 5 in the cosmic microwave background, if you can arrange such that there's some very enhanced density fluctuations at much smaller scales, and if those density fluctuations are large enough, then they can collapse to form black holes, and that's what a primordial black hole is. And the probability for it to collapse is related to how high this density fluctuation is. The actual mass of the black hole is related to the wavelength of this overdensity, where you have more matter inside of some particular wavelength. Now, in terms of actually getting charges in the black hole, I'm not going to put any equations or anything. I'm just going to schematically draw it and refer you to this Katie Free's paper that I was mentioning before, as well as my previous paper, if you want to know a little bit more about this. But essentially, what happens is you can have both some charge imbalance in the collapsed region itself. So the black hole collapsing in some region that happens to be just have a little bit more positive than negative, or vice versa. And then after that, the black hole is going to traipse around, or more specifically, the plasma is probably going to be coming in towards it, and it'll be absorbing both positive and negative charges. And of course, on average, the black hole will get 0 charge, but the typical fluctuation away from 0 is just essentially just a 1D random walk. gives you that the typical fluctuation is of order the square root of the number of charged particles that it absorbs. And yeah, so this is just one possible way that these could be produced. As we said, maybe there's some other exotic ways that could be produced early on in the Big Bang. And I'm not going to get too much into that. The main thing that I want to focus on is just whether these relics, if these relics were to exist, how would we know that they're there?
Sorry, I have a question about this random walk picture.
Yeah.
So initially, if we assume that the charge is neutral, then I can imagine that's a random walk. But when it is getting to the extremal black hole, then the repulsion become important. In that case, then it gets harder and harder to accumulate more charges of the same sign.
Good question. So actually, it doesn't end up becoming that much harder because as long as the black hole has not yet evaporated down to near extremal. So as it's absorbing charges, its mass is still much larger than its charge. And of course, for the actual charge carrying particles, it's the opposite. Their charge is larger than their mass by the weak gravity conjecture. But if the ratio of the charge to mass for the black hole is sufficiently large, then the main thing that the charged particles are going to see is actually the gravitational attraction, and not the E&M attraction or repulsion.
I see. Thanks.
Okay, so that's all I'm going to say about formation for now. So now let's start talking about some of the bounds that one can place on these relics. So we can start by thinking about bounds that are placed on regular particle monopoles as opposed to magnetic black holes. And one of the first places to go over that is the Parker bound. So the Parker bound was initially developed in the 70s, and the idea is that if you have some monopole that's passing through your galaxy, and it passes by some region that has some coherent and large magnetic field, then as it's going through, it's going to take energy away from that magnetic field. So it's going to gain some velocity, and of course, so any energy that the monopole gains is subsequently lost by the field. And so if you have a bunch of monopoles going through this region, then you can completely deplete this B field to where it would go away. Of course, we observe large-scale magnetic fields in the Milky Way, and so we can set a bound on the flux of monopoles that are passing through this region by demanding that those regions are not depleted. So to put this in an equation, we say that the amount of energy that's picked up by the black holes or the monopoles times their flux times the size of the region, so the total number of particles going in per unit time has to be, and then times the amount of time that it would take to regenerate that field has to be less than the total energy contained in that coherent region of magnetic field. Now, a little bit of magic happens here for magnetic black holes. So normally, there's this factor of mass here that cancels with a factor of mass in the flux. So more, if the mass is larger, then there's fewer particles, and so the flux is so to keep the flux constant. But then this delta V depends on the charge divided by the mass. So normally for gut monopoles, the charge is just equal to 2 in these units. And so normally there's some mass dependence from this bound. But because for extremal black holes, the charge and the mass are directly proportional to one another, there's actually no charge or mass dependence whatsoever once you take this full expression. So in effect, you can set a bound on black holes as a fraction of dark matter that is completely independent of the charge or the mass, and only depends on quantities related to the actual related to the galaxy. So the velocity of the virial velocity, the local density of dark matter, and the properties of the actual coherent region of B field, the coherence length and the time it takes to regenerate. And you can see this falls just short of doing anything useful. So obviously we would want to constrain this as a fraction of dark matter. So we want this number to be less than 1 if we want an interesting constraint. And so this is the classical Parker bound as applied to magnetic black holes. So because this is so close to being useful, but not quite, we wanted to think, is there any way that one could get a stronger bound using some other system? And so in particular, the main constraints are this coherence length and the timescale, the regeneration timescale. For the Milky Way, I've shown here just some depiction of some of the large-scale magnetic fields that happen in the Milky Way, and you can see that they're kind of not really all ordered very nicely. There's some going in one direction, some going in opposite directions. And it turns out also the regeneration time is directly related to the coherence length. So the longer the coherence length of these magnetic fields, the more time it takes to generate them, as you may expect. And this is under some dynamo action model of generating these magnetic fields. So then, since these two are so directly correlated with each other, we just need to find a system that has larger coherent magnetic fields. And it turns out that our next door neighbor actually is a very good candidate for this. So if you look at the Andromeda galaxy and you make a map of its magnetic fields, it's all very nicely actually symmetric and all very nicely pointing in the same direction, essentially. So if you have black holes that are orbiting in this galaxy, then they would drain away this very well ordered magnetic field, and you wouldn't measure it to be like this. And so you can extend the Parker bound, actually we found, by many orders of magnitude to, instead of these to full galaxy size correlation lengths and a matching regeneration time. And if you do that, you get a much stronger bound, saying that these can only be about 10 to the minus 4 of dark matter. So that's in some ways exciting, right? We've gotten a much stronger bound than what we could have before. Of course, on the other hand, it's a little bit disappointing because now we know that regardless of mass, there's no way that these can make up all of dark matter. So you may ask, is there really much more story to tell? Should we still care? Should we still search for them? And as I've tried to argue already, I think we should still care about them because they are states that, as I said, exist in principle only with with standard model and general relativity. And so we should ask if there are ways that we can do better than this Parker bound, and see if there are any such relics around, because they would still have very fundamental implications for particle physics. And so again, as I previewed, we're going to look for places where we can have a lot of these mergers, or these so-called what I'm calling annihilations, and where we can have a lot of baryon number violations. And it turns out the best place to look for these sorts of things are in dense media, where you can get a lot of these things together and promote these processes to happen much quicker in a small amount of space. And so that would in particular be sun, Earth, or neutron stars. So let me talk about capture in the sun first, and a lot of the other things are going to follow somewhat straightforwardly from that. So parametrically, the stopping power of a monopole inside of dense materials is given by this expression. This was studied extensively in relation to ordinary monopoles for many decades back. Relates, of course, to the scattering cross-section, which is the electric charge times the magnetic charge squared. Relates to the density of states and the Fermi velocities or thermal velocities and the mass of the particles that are being scattered. The important thing to note here is that for a magnetic black hole, the stopping length decreases in the same material decreases as Q increases. So as long as Q is greater than some Q min, the magnetic black hole will always be stopped in whatever astrophysical body that you want to consider. And so you can see in general, most charges will be stopped by the sun, the Earth, and all charges will be stopped by neutron stars. So then we can start to treat this essentially the same way that we do WIMP capture in stars. So you can define some capture rate going as the area of the star and the flux of monopoles coming under the star, and you can then ask, okay, well, if they annihilate quickly enough, then the annihilation and capture rates reach an equilibrium, and so that the annihilation rate is just equal to half the capture rate. And then the only question remaining is whether or not they reach equilibrium. And the answer is different for different systems, whether you're talking about the sun or whether you're talking about neutron stars. So let's stick with the sun for now. Normally what we do is we say, is we compare essentially the gravitational energies and the kinetic energies, and we ask how likely is it for two particles to be close enough together that they annihilate. However, here, because we're dealing with a magnetically charged object, we also need to take into account the magnetic field of the sun. And this was fleshed out quite a bit by Katie Fries and others in the 80s. So essentially, what you could think of happening is if there's only a few monopoles and antimonopoles, they'll actually want to be separated from each other by this constant B field if they're in the core of the sun. We're going to model it as an approximately constant B field inside the core. And so then, if there's only some of them, they will stay some distance apart from each other, and they'll never be able to. And ones that are of opposite charges are never going to be able to find each other and annihilate with each other. So we can write down this force balance equation. And you can write down the repulsion from the due to the constant B field, and the attraction due to the gravitational force from the solar material, and then also the attraction from the monopoles to the antimonopoles. And this is actually just twice the gravitational attraction. Again, just because the magnetic field or the magnetic force between two oppositely charged magnetic black holes is approximately equal to the gravitational force. As I said, if n is small enough, if the number of black holes is small enough, then the first two terms can balance. But once the number becomes large enough, then this third term dominates, and the whole system collapses. And it turns out that that as long as they make up greater than about 10 to the minus 11 fraction of dark matter, then you always have you always reach this critical number to where they're able to efficiently annihilate with each other. And this is again independent of the black hole mass. Okay, so good. So at least in the case of the sun, we do have some equilibrium between the capture and the annihilation. And so now we can ask what sort of signal we should look for. So once they do start to Hawking radiate, they're going to radiate charged particles, muons, mesons, taus, charms, bottoms, all these sorts of things. And those things are going to, in turn, decay or cascade into neutrinos, high energy neutrinos. And we can look for those high energy neutrinos at experiments like IceCube, which begin looking for neutrinos starting at 10 GeV. So then we only have a few requirements. We need for the temperature of the Hawking radiation to be large enough that you see these, so that it has to be at least 10 GeV. And you also need there to be a short enough time between annihilations such that you observe an annihilation during the observation time. So we looked at a 3-year observation run with IceCube, and then compared essentially the flux of neutrinos that we would expect from this Hawking radiation to the flux that's observed by IceCube, and we're able to set a bound. I will caution that, and we spell out in great detail how we do this in the paper. We took some simplifying assumptions here, and the main problem here is that the sun is actually opaque to neutrinos that are higher than about 100 GeV, and so you need to treat the lighter mass black holes that radiate at higher energies with a little bit more care. Ideally, you would do some full numerical simulation of the neutrino propagation and scattering and all of that through the sun. We were not advanced enough to do that sort of detailed numerical calculation. So we took some simplifying assumptions about the neutrino multiplicity to reach this result. But we think it is broadly representative of what you would expect. And a lot of this result is, of course, at least the bottom lines are limited by these two conditions above here. So
just a question here, what does the flux look like?
Right.
As a function of neutrino energy?
Right. So as I said, the flux coming out of the sun has to be less than 100 GeV, right? Because it's just opaque to anything above that energy. So essentially, we said that as the particle is interacting with other particles in the sun, it's scattering and creating more, like cascading and creating more and more lower energy neutrinos. So we took the multiplicity of those lower energy neutrinos to be directly proportional to the energy of the initial initial particle that was produced.
But it's like a box function, or like, is there a sharp decrease?
Right. Yeah, there's kind of a sharp cutoff
Okay.
at least that's how we approximated it. As I said, we didn't do the full numerical simulation.
Okay, thanks.
Okay, so at this point we can take a step back and start thinking about making a plot of the bounds. So before anything I've told you, the thing that you could have obviously drawn on here that you would have known right away if you thought about black holes at all were these microlensing constraints. This is Macho, Eros, Ogle, Kepler, and HSC Subaru. And so these are looking for black holes passing in front of stars and causing them to become temporarily brighter as they pass in front. And then, of course, you would have said anything below this red line, anything to the left of this red line would have evaporated, and we wouldn't even bother to look for them. And I've taken off some evaporation constraints here for now, of course, but there's some other evaporation constraints for ordinary black holes that don't apply to magnetic black holes because of this enhanced Hawking radiation. So then I told you before that we had this that we strengthened the Parker bound by looking at Andromeda, and we rule out all of this region at the top of the plot independent of mass. And now if we also add on this ice cube constraint that I just told you about, then we can actually exclude quite a bit more from this plot than what you can do with the Parker bound alone. And just to reiterate what these various regions are, on the left is where the particle or the black holes are no longer able to capture to the left of this line on the sun, so they pass right through without stopping enough to be captured. Of course, we've drawn this as a vertical line. Of course, there really should be some tail here instead of a straight vertical line from doing the proper Boltzmann distribution of the velocities, but this is close enough for our purposes here. The bottom is limited by the observed flux, so that's just comparing the number of neutrinos you expect versus the number that you observe. The slanted portion is where the time between annihilations would exceed your observation time. And then finally, at the top is where the Hawking temperature is too low and you wouldn't detect these neutrinos at all at ice cube. So that kind of gives us a prototype for how we can think about neutrinos from the sun and also from Earth. So without being in interest of not being too repetitive, let me start to fill in this plot with a couple of other things that you can look for neutrinos from. So you can extend at higher masses, which corresponds to smaller Hawking radiation temperature. You can extend this using, say, lower energy experiments with lower energy thresholds, such as Super K, and which also happens to be running a little longer than ice cube. And extend this down here. Of course, this is below still the Parker limit. You can also think about capturing on Earth and looking for neutrinos coming from Earth, from ice cube. And so that's shown here, a little bit subdominant to the sun. And another interesting thing you can do is ask whether the amount of energy produced by these black hole annihilations exceeds the amount of geothermal heat that we observe coming from the core of the Earth. And you get some other box constraint here. So that wraps up the constraints from the sun and the Earth. And so now let me move on to constraints coming from neutron stars. And neutron stars turn out to be qualitatively very different from the sun in terms of what happens inside of their cores. So the first zeroth order thing that I need to say is that we're going to be interested in what happens inside of the cores of neutron stars, because that's where the black holes are going to end up once they're captured. But in truth, we don't actually know very much about what happens inside of the cores of neutron stars. We have a pretty good sense of what happens at the crest of the neutron star, and going in maybe even to the outer core, we have some sense that there is some superconducting proton phase. But then once we get into the inner core, there's really just a lot of different models for what could happen, and we don't have a very good sense. There could be some Pion superconductors, some other quark states. There could be some quark superconducting, color flavor locking, all sorts of different things. So everything that I'm going to say about neutron stars is going to be very much dependent on exactly what the details are of what's happening in these neutron stars. Still, it's going to be worth looking at least a little bit, because in principle, if we had more information, we could set much tighter bounds by using neutron stars. So the main phases that I'm going to talk about are proton and pion superconductors. So if the core region is in one of these phases, then these superconductors, of course, want to expel magnetic fields. They don't want magnetic field lines passing through them. But if you force there to be some magnetic fields there, say by sticking a magnetically charged object, then all of the magnetic fields are going to be confined into flux tubes. And these tubes are very, very compact. They have a radius of order the London penetration depth, which in these dense media are very small, 10 to the minus 12 centimeters. And each one carries a unit of magnetic charge or magnetic flux, excuse me. So each magnetic black hole has Q different flux tubes coming out of it. So as a result of them being so small and having this unit flux, the magnetic field inside of them is very, very large, 10 to the 16 Gauss. And their tension is each tube has a tension of order 10 to the 4 Newton. So then you can ask, whether you can have some configuration that looks like this, essentially, where the force from the tension force from these flux tubes balances the gravitational attraction to the stuff inside of the core. And in fact, you do. So for these Q different tubes, each with some tension force, comparing that energy to or that force to the force of gravity, these are stabilized about 1 kilometer outside of the center of the neutron star. So very, very much in the center of the neutron star core, whereas I said, we don't know a lot about what's happening in that region. And yeah, and there's a lot of work, of course, has been done on this in the context of ordinary monopoles. Here's just one paper that talks about this. So the upshot here is that this is basically the exact opposite of the or it looks like it could produce a situation that's the exact opposite of solar Earth capture, where instead of the black holes finding each other and annihilating, they just kind of hang around inside of this neutron star. We still need to, of course, do an estimate to make sure, or to see when these annihilations become important. So annihilations could happen essentially if the flux tubes from one black hole meet up and connect with the flux tubes of another black hole, so that you get flux tubes that are connected to between black holes as opposed to being connected to the surface of the core. So you can estimate how often these sorts of meetings happen. You can, first off, one quantity that you need is the opening angle of the flux tube, which is related to the tension in the tube and the thermal energy from that the tube has. So how much it's able to spread away from being exactly straight up and down. And then you can calculate the encounter rate of one bundle of flux tubes with another bundle of flux tubes based on their two-dimensional cross section and their density, their thermal velocity. And then finally, you get some annihilation rate, which is related to both this encounter rate and the probability that enough of the flux tubes connect to each other to where there's more attraction between the two black holes than there is attraction to the sides of the core. There are regions where you do get some equilibrium, and some regions where they essentially never find each other, and you're just building up more and more black holes. So I'll spare you the gory equations, but essentially the number of black holes that are hanging around is either going to be some equilibrium value where it's the rate captured times however long it takes to get to equilibrium, or it's just going to be the total number that were captured over the lifetime of the neutron star. And here we're talking about, by the way, very, very old neutron stars, where they spent the majority of life as neutron star, and so this is the dominant effect. Okay, so then once they're hanging around, then we can ask about the luminosity that's generated from these black holes absorbing the neutron star matter and then re-emitting as Hawking radiation in these so-called, or what I call baryon number violating processes. Now, the neutron star is, of course, much more opaque than even the sun. So you're never going to actually see the direct emission from one of these black holes getting all the way up to the surface. And so you need to relate the emission that you get at the black hole to the emission of photons at the surface, because these are much more distant. There's really no hope of seeing neutrinos coming out. So you really just need to see what the relationship is between the luminosity here and then the luminosity of photons at the surface of the neutron star. It turns out that for this is very dependent again on the exact nature of the matter inside of the core of this neutron star. So if it's a proton superconductor, it turns out that most of the energy that's released by the black hole will eventually be emitted as photons. This ratio is of order 1. Whereas if it's a pion superconductor, for instance, much less of the energy ends up as photons. A lot more of it ends up as neutrinos. In any event, once you know that, then you can compare the luminosity that you get from these Baryon number violating processes to limits on the X-ray luminosity from neutron stars. And there's a lot of different ways that you can constrain this, and a lot of work that has been done on this. Just to give a sense, you don't need to read all this table, but just to give a sense, there's a lot of different ways that you can do this, and they all have advantages and disadvantages. So you can look for the diffuse X-ray background coming from all of the neutron stars in the galaxy. You can look at X-ray emissions per neutron stars. You can look at very, very X-ray quiet neutron stars, individual neutron stars. You can look at individual pulsars. There's lots of different ways you can do this. So, but the upshot is, because of this, it's a fairly robust bound that you can set on the overall luminosity. So finally, then going back to the slide, if you compare the rate that you expect versus this limit that came from all these various different ways of measuring this, you can set some constraint from neutron stars, which I've indicated in dashed. Now it's dashed instead of solid because, again, this is very dependent on the exact nature of the materials in the core of these stars. But here at least is some demonstration that you can cover quite a bit larger mass range below the Parker bound than what you can just do with the sun or the Earth. So on the left is where annihilations and capture equilibrate. Here is where it's suppressed. It's not really suppressed. It's just that annihilations are rare, so you're essentially dominated just by every single black hole that you've ever captured. And then finally, you need some. On the right is the requirement that you have neutron stars capturing at least some black holes. And you can see also the difference here between the R equals 1, which was for a proton superconducting core, versus R equals 10 to the 4, which was kind of the pessimistic value for a pion superconducting core, just to see some of the variation that's possible in this bound. One final thing that you can do is look for essentially direct detection of black holes passing through materials here on Earth. So you can use dedicated monopole experiments like macro, which is schematic is shown here on the left, or you can look for tracks of charged particles running through these ancient minerals, ancient mica minerals. And if you do that, you can add a couple more lines to this plot at the very low masses. This is just kind of short of competing with the Andromeda Parker bound down at these minimal black hole charges. Okay, so how am I doing on time?
So we are over 12 minutes. I guess, okay, we had some discussion, but just to let you know the time.
Okay, good. So let me go ahead and wrap up kind of at this point. So I have this slide that's promising some other things if we had time, but since we don't, let me go ahead and wrap up at this point. So just to summarize, what I've told you so far is that black holes are interesting new states that in principle require new physics. Of course, their formation may require some additional physics like gut scale monopoles, or maybe some other more exotic way of producing them in the early universe. There's lots of ways that we can constrain them. Some of these are learning from ways that you constrain ordinary monopoles, and other ways, and but then you extend them, or they change appreciably once you think about the charge to mass ratio essentially changing, and also the effects of this Electroweak-symmetric corona changing how these black holes essentially decay via their Hawking radiation. And of course, if we were to detect something, this would essentially constitute the first time that we would ever detect Hawking radiation, which is also kind of a neat aside for if these relics were to exist, that one could probe other parts of fundamental physics as well. So yeah, I'll wrap up there, and thanks for your time.
Yeah, thank you. We'll thank you with some virtual claps here. Are there any questions?
Yeah, so I had a question then. So you basically worked with this extremal black hole metric, but what would happen if you also allowed for spin and rotation for these objects?
Yeah, good question. So it turns out that if you, let's see, I'm not sure actually for objects as heavy, to be honest, but in general, if you just say assume if you just talk about an extremal black hole that doesn't have any charge, that only has angular rotation, one that's near extremal, the Hawking radiation is actually fairly good at sapping away the angular rotation, as well as it approaches to near extremality. So as it gets closer and closer to extremal, the angular momentum would get sapped away by the Hawking radiation, and then it would just continue on to Hawking radiate down to, I guess, either down to a Planck scale relic, or if it has some magnetic charge, then down to its extremal state with just charge.
I see. So then, but would your limits also change then as well, right? You would also,
well, because it's so good at getting rid of the Hawking radiation, or sorry, getting rid of the angular momentum via Hawking radiation. I wouldn't expect that this would appreciably change the mass to charge ratio in this case.
okay.
So turning to this neutrino flux, is the capture frequent enough so that it occurs continuously, or it occurs in bursts?
Yeah, so that depends a little bit on the, let's see.
In the Earth, for example.
Yeah. Oh, okay. Sorry. So good. Sorry, I was thinking of Baryon normalization. Yeah, for the annihilations, it can occur in maybe the quickest way to see where this becomes important is along this line for the sun bounds. So if you have either more massive or fewer smaller fraction of black holes being dark matter, then the time between annihilations here exceeds the observation time, which for this particular ice cube study was 500 and some days. So I guess 1.5 years total observation time. So yeah, that gives you a sense of like where it becomes more sporadic. Now for the Earth heat, it turns out like the Earth is obviously very slow at conducting heat from the core the crust. Otherwise, we would all be frying right now because the core is much hotter than the crust. So it doesn't matter so much for Earth heating in particular how sporadic it is, because it kind of takes a while to diffuse out from the core. But of course, it does matter more for these ice cube and super K experiments.
I was wondering if you could have a burst of events.
Yeah, definitely. So at this at the rightmost part of this plot, if we run ice cube for longer, obviously we are. If we just wait, say they actually do exist, at this point in the plot, then you would see a big burst of events, sometime in the next few years or something, just from one single
The
annihilation.
last question I had: do you expect any magnetic disturbance from passing black holes, like in magnetometers and so on?
Sure. So that's something that I'm still kind of thinking about and interested in. Something in particular that I'm working on, actually getting close to finishing, is it turns out that no one has bothered to measure the monopole moment of the Earth to see if the Earth's field has a magnetic monopole. So you can actually look to see if there's some net monopole charge and magnetic monopole charge in the Earth using satellite magnetometers, and we're getting close to finishing that. And you can get some non-trivial bound somewhere kind of in this region by looking at that.
Okay, good.
So maybe it's a stupid question, but if it's, inside of the sun, wouldn't it be pushed to the surface at every now and then, and therefore would be able to annihilate into neutrinos that are a higher energy that you can search for? I'm not sure because of the numbers of the magnetic field that you have. I didn't check, but
No, it's still heavy. It will settle in the right.
Yeah. There's some competition between the amount of energy and the gravitational potential here, right? And because they're so heavy, there's their kinetic energy is very small, and so they're going to want to very quickly settle into the core. Now there is some time frame that it may take them to get to the core initially, right? So like when they first come in and get captured, it may take them a little bit of time to drift down to the core, but I think in general they're always going to want to move towards the core.
Hi, Nick. I have a generic question.
Yeah.
So in the beginning, you introduced this magnetic charged black hole, and there will be a corona of electric phase and even a QCD phase. But in the rest of your talk, we are not using any of the effect of those coronas, right? We're really just detecting a magnetic charged black hole using any generic property of that. So are they just separated? So in that sense, you are not really trying to see the electric relic of our universe in some sense.
So we are using it in a few ways, indirectly, of course, as you say. There, for none of what I've really talked about here is directly probing it, but indirectly, we are seeing it, for example, in the neutron star bounds, and that any particles that get inside of the corona, we assume follow these 2D modes and ultimately get absorbed by the black hole. So it's kind of increasing the cross section for the capture of particles inside of the neutron stars. So that's one thing that's doing. Of course, the other thing that it's doing is it's enabling these very, very quick Hawking radiation, which if the corona wasn't there wouldn't be present. But yes, you bring up a good point, and that's kind of where, if I had a lot more time, which I knew I wouldn't, but if I had a lot more time, I would tell you a little bit more about how you can make the basic problem. The reason why that we're not really looking at the coronas themselves is that the number density of these things are very, very small still, right? They're very, very massive. So the chances of them going through your detector in your lab or through like these ancient mica samples are just very, very small. But if they were allowed to be much smaller than the Planck, their mass were allowed to be much smaller than the Planck mass, then you could look for the effects of these coronas directly in a lab. Yeah, as I said, way too many slides here. But essentially, what you can say is that as the radius of these of the corona increases beyond about one inverse GeV, it's going to have some very strong reactions with nuclei that it passes by. And once it becomes large enough, essentially this saturates to a geometric cross section. So just going as pi r squared. And so then you can look for some interesting signals from, say, in xenon. You can look for single hit or multi-hit scattering in xenon. You can look for it in neutrino detectors like Juno. And here again is mica. So, or you can also look in super K or hyper K. Lots of different things that you can do there as well. So thanks for asking, so I could at least show a couple of these slides.
Good. Yeah, I guess the impact are more on direct detections essentially, right? Where the corona enables a stronger interaction with our ordinary field.
Yeah, and then so something that I'm not even showing here is like you can also form bound states. So if the proton becomes massless once it gets inside, then it can radiate a photon and form bound state. And there's a lot more there that one could say. Once their number density becomes small enough large enough that you can actually see them in your lab.
Thanks.
So I have some questions about the phenomenological consequences of these magnetic black holes. Have you thought about, hypothetically, if two collide, right, the chance is probably very, very rare. But if they do collide, what would be the signatures in the neutrinos and so on? Yeah,
good question. So the question is not so much what happens if they collide per se. If I'm being picky about the wording, it's they really do form into binaries, just like just like black holes that are relevant for LIGO or that sort of thing. So the question then is how often do they form into binaries? How often do the binaries merge? And then what's like kind of the net neutrino signal that you can get from that? And that is something that we talked about in this earlier paper that I referenced when I talked about the formation of extremal charged black holes. And there actually you can get a pretty strong diffuse neutrino signal. We did a very crude back of the envelope estimate, and it seems like actually you could get constraints that are maybe a bit stronger than this Parker bound as well for that sort of merger. But it's our estimate was so crude that like I had that we didn't really want to put it on the spot just because it was not to the level that we felt we could really put a solid line anywhere on the spot.
Okay, thanks. And another quick question is, have you thought about the super radiance signal if you have axions around this magnetic black holes?
Yeah, I haven't really thought about it. Okay. Yeah, I don't have too much. I mean with super radiance, like the constraints, like to at least today are mostly from once you know what the black holes are. Well, once you know that they're looking at their spin, right, and looking at how likely they are to have so looking for the absence of black holes with high spin. So I don't know exactly how you would translate that to this, but I don't know if there's some sort of super radiance laser effect that one could do or something. I'm not really sure. I haven't thought of it too much.
Thanks.
Any more questions? If not, then we can thank Nicholas again